Hello friends, as a part of online lecture series on the subject signals and system, today I will start the point systems and its properties. In the last lectures we have seen what do you mean by signal, basic signal definitions, then we have seen the basic types of the signal, we have also covered the basic operations done on the signal. Today we will see system and its properties. So let's start this session. So basically what do you mean by system? A system is the process the input signal to produce the output signal. Means it is the basic block for which we are going to apply the input signals and we are going to get the output signal. So for example, any electronic circuit, so you consider the circuit involving the capacitor in it, so it can be considered as the system because it is going to transform the voltage source to the voltage signal across the capacitor. Means we are going to apply the input for that circuit and we are getting the output voltage there. Means it is an example of system. Now the next example, you consider the CD player. So CD player takes the signal on the CD and transforms it into a signal sent to the loudspeaker. Then the best example of a system is the communication system. So basic communication system is consisting of the three subsystems. First is the transmitter, then the channel and the receiver. So the channel typically attenuates and adds the noise to the transmitted signal, which must be processed at the receiver end. So the communication system, it's the best example of system. Now the standard definition of system, it can be defined as a system is a physical device, means it's the combination of elements, or it's an algorithm that manipulates one or more input signals excitation to accomplish a function, and it is going to produce the output. That output is either one or many outputs. So this is the basic definition of signal. So system takes a signal as an input and it transforms it into another signal. So you can observe here. So inputs are applied to this system and we are getting the output signal here. So depending on the type of signal, the systems can be classified as continuous type system or discrete type system. So basic types of systems. So these are the basic types of system. So first is the static and dynamic system, then causal and non-causal system, then time variant and time invariant system, linear and non-linear system, stable and unstable system. So we'll see all the system one by one. So first, static and dynamic system. So for the static system, its output signal depends on the present values of the input signal. A static system, it is a memoryless system. It is not having any storage devices within it. So these are the examples. So we can observe these equations here, signal equations. So I of t, it is equal to 1 by r v of t, means current, it is equal to voltage upon resistor. So it's an static system because as you vary the voltage and resistor, accordingly we are going to get the current there. You also observe this equation, second equation, that is y of t, it is equal to r of x of t. So x of t is the input, r is the any input constant number there. So the input signal multiplied by constant number, so we are going to get the system there. So it is the y of t, and you can consider this as a static system. You also consider this example y of, means discrete signal example, as y of n, it is equal to squared function of 2 into x of n minus x square n. So it is the basic static system examples. Now the dynamic system. So for the dynamic system, output signal depends on the past values or future values, or both past and future values of the input signal. So dynamic system, it is the system having memory. It has storage devices. So we can observe the examples of this dynamic system. So y of t, it is equal to txt plus 3xt square, where xt is the input, t is the time parameter. So you can observe this y of t. So what the y of t you are going to get, it is dependent on the time, and it is going to vary with respect to time here. So we can say it is the dynamic in nature, means it is having memory, because at each and every instant of time it is going to store the information there. Again, you can observe this second example equation here. So y of t, it is equal to 1 by c integration minus infinity to t x of t dt. So you can consider this for the capacitor. So for that capacitor, we can write here v of t equal to 1 by c integration minus infinity to infinity I of t dt. So likewise, you can write the equations for dynamic system or system having memories. As far as discrete is considered, so you can observe this equation here. So y of n, it is equal to x of n minus 1. Then we'll see the next system type, that is causal and non-causal. So the causal system, a system is said to be causal if the present value of the output signal depends only on the present and or past values of the input and past values of the output signal, but it is not depending on the future input or output values. So these are the non-anticipative system, because output is not anticipated here, future values of the input, means the system is not going to anticipate the future values of the input. So you can consider the example here, y of n equal to x of n plus 0.5 x of n minus 1. So this is the system example of causal system. Non-causal system, a system is said to be non-causal if the present value of the output signal depends on any future values of the input or output signal. So we can observe the examples here. So y of n, it is equal to x of n minus 2 plus 0.5 x of n plus 1. Y of n is equal to x of n plus 0.5 x of n plus 2, means output depends on any future values of the input here. So we can observe n plus 1 or n plus 2 here, means these are the future values. So again, these are the some of the examples of causal and non-causal system. So you can observe here, y of t, it is equal to 1 by c integration minus infinity to t x of t dt, or y of n is equal to x of n minus 1. For the non-causal system, you can observe this example, y of t, it is equal to x of minus t, or y of n, it is equal to 1 by 3 x of n minus 1 plus x of n plus x of n plus 1, means output is dependent on the future values also. Now we'll see the next, that is time invariant and time variant system. In the time invariant system, so a system is said to be time invariant if a time delay or time advance of the input signal leads to a identical time shift in the output signal. So you can observe here, so x of t is the input signal, it is delayed by t0. So x of t is passed through the delay, then we are going to get x of t minus t0, and it is applied to the system, means one function, and we are getting the output as y of t minus y of t comma t0. Then you observe this second block diagram here. So here x of t is applied to a system and we are getting the output as y of t. This y of t is delayed by t0, then we'll get output as y of t minus t0. Then if this y of t comma t0, it is equal to y of t minus t0, then definitely it is a time invariant system. Now we'll see what do you mean by time variant system. A system that is not time invariant is said to be time varying. A time variant system is a system whose behavior changes with respect to time. So compared to time varying systems, a time invariant system are much easier to design and analyze since their behavior does not change with respect to time. We'll see one example for time invariant or variant system. So consider this example, y of t equal to sine xt. So we'll find out whether this is time variant or invariant. So let us determine the output of this signal for delayed input of x of t minus t1, means we are going to write the output y of t as delayed output for the delayed input. So y of t comma t1 must be, we are going to delay in the x of t now. Therefore sin x of t minus t1, so this is our delayed output. For the delayed input we are going to get this output, let it be y of t comma t1. Now we will delay in the output yt by t1, so therefore y of t minus t1 will be what, sin of x comma x of t minus t1. So on comparing these two equations we can write y of t comma t1, it is equal to y of t minus t1. So therefore this given example, that is y of t equal to sin xt, it is the time invariant system. Now these are the some of the examples mentioned here, time invariant and variant system. So you can observe this. So y of t equal to t x of t, or y of n equal to n x of n, it is the example of time variant. Similarly yt equal to 2 e raised to xt, it is the example of time invariant. Y of n is equal to 2 a raised to x of n, it is the example of time invariant. So later we'll solve all these examples to verify whether these signals are time variant or time invariant. Now we'll see the next system, that is linear and non-linear system. A system is said to be linear if it satisfies the principle of superposition. So for checking the linearity of the given system, first we have to check the response due to linear combination of input. Then we have to combine the two outputs linearly in the same manner as the input are combined, and again total response is checked. If the response observed in about two steps are same, then the system is linear, otherwise it is said as non-linear. So the same can be written mathematically as y1t equal to function of x1t, means x1t is the input and y1t is the output. Similarly y2t, it is equal to f of x2t, means x2t is the input and y2t is the output. Now if we multiply this x1t by any arbitrary constant a1, and if you multiply x2t by any arbitrary number or constant number a2, and if we add these, then we are going to get function a1 x1t plus a2 x2t. If this is equal to a1 y1t plus a2 y2t, then we can say the system is linear, else the system is non-linear. Now consider the example yt is equal to x square t. So the output of the system, so we'll write the equations for two inputs x1t and x2t. So let y1t is the function of x1t, so it can be written as x1 square t. Similarly y2t is the function of x2t, so it can be written as x2 square t. Now we'll do the linear combination of these two outputs, so these two inputs, so this will become, so let y3t is the output. So y3t, it is equal to a1 y1t plus a2 y2t. So we'll put the values of y1t and y2t here. So this will become a1 x1 square t plus a2 x2 square t. Now we'll find the response of the system to the linear combination of inputs. So let that output is y3 dash t, and it is the function of a1 x1t plus a2 x2t. So our function is squared function here, therefore what the combination you assumed here, you take the square of that, therefore it will become a1 x1t plus a2 x2t bracket square. So if you simplify this, you will get the output as a1 square x1 square t plus a2 square x2 square t plus 2 a1 a2 x1t into x2t. Now if you can observe here, y3 dash t is not equal to y3t, so hence it is not going to satisfy the principle of superposition, therefore it is the non-linear system. Now we can observe some of the examples here. So these are the linear examples, linear system examples, and these are the non-linear system examples. So we'll try to solve this in the next session, these problems. Now we'll see the next system, that is stable and unstable system. A system is said to be bounded input bounded output stable, that is BIBO stable, if and only if every bounded input results in an bounded output. So example you can consider here, y of t is equal to a of xt. So a is the any arbitrary number which is greater than 1. So this particular system, it is the unstable system. Why? Because if we assume x of t as any signal, for example consider x of t as unit step signal, then at every instant of u of t, means at every instant of unit step signal, will keep on multiplying it with the number a, and it will not be bounded. It is not in a limited, it is unlimited value. Therefore we can say this y of t equal to x a of x of t is a unstable system. We'll consider the next system. We'll verify whether this system is stable or unstable. So consider the example y of t equal to e raised to x of t. So here y of t is the output and x of t is the input, and the function is exponential function. So here assume capital B be the any positive number, and for this any positive bounded capital B number, let x of t is the input signal, and it is going to satisfy mod of x of t, it is less than that positive number capital B, or if it satisfies mod of x of t, if it is going to lies in between minus b to plus b, then the output y of t must satisfy this condition, and this condition is this y of t must lies in between e raised to minus b to e raised to plus b. So if it is going to satisfy this condition, then we can conclude that if any input to y of t is bounded by a positive number b, then corresponding output is how to be bounded by e raised to b. So we can say for the bounded input we are getting bounded output, therefore this given system is a stable system. Now we'll see the last type of system, that is invertible and inverse system. If a system is invertible, it has an inverse system. So for example consider this block diagram here. So x of t is the input, it is applied to the system, we are going to get the output as y of t, and if we apply this y of t to the inverse system, then we must get here x of t. So if the system is invertible, then it has an inverse system. You can consider this as an example here. So y of t is equal to 2 of xt, where xt is the input and y of t is the output. So the system is invertible, it must have inverse. So for any x of t, we get the distinct output yt. Thus the system must have an inverse system. So we can write x of t as 1 by 2 y of t, and it is equal to z of t. So you can observe here, so x of t is the input signal we apply to the system, so that let that system is the multiplying system. So we'll get y of t as 2 of xt. Now we'll apply this y of t to the inverse system. So it is the divider system, so it can be divided by number 2, so it is, or you can say multiplied 1 by 2. So 2xt into 1 by 2, so it definitely will get output as x of t, means the system is invertible and it is also having the inverse system. So likewise the basic systems we have seen. Now in the next session we'll solve the problems based on these systems. For time being we'll stop here. Thank you.